Hello and welcome to the BS Academy. We hope that your preparation is going well. So let's start the next video.
Now in the third chart of the fluid mechanics, we'll include the boundary layer theory, then after the dimensional analysis, and at the end the hydraulic turbines.
Before that, if you are new to your academy, then please subscribe for the upcoming videos and the links for the short notes which are in description box.
So in the boundary layer theory, here you can see that basics. First one is external flow. It is the layer near to surface. Boundary layer is generated, and inside the boundary layer shear stress and drag force is not neglected. The flow is governed by the Navier-Stokes equation. Then the region outside the boundary layer is almost constant velocity, and velocity gradient du by dy is equal to 0. Then shear stress is also equal to 0. Then this flow is treated as the ideal flow and governed by Euler's equation. Then after displacement thickness delta star, it is defined as the distance normal to surface such that the mass flow rate passing through this distance corresponding to the ideal fluid is equal to loss in mass flow rate due to formation of boundary layer. Here the equation for the delta star is equal to integration 0 to delta into 1 minus u upon u infinite into dy. Then momentum thickness theta is equal to integration 0 to delta u by u infinite into 1 minus u upon u infinite into dy. Then drag force is equal to momentum lost by the fluid per unit time. Fd is equal to rho b u infinity square into theta, and t omega x is equal to rho into u infinite square into d theta by dx. Here t omega, or you can say that tw or whole, and this equation is known as the von Karman momentum integral equation. And energy thickness delta E is equal to integration 0 to infinity u by u infinite into 1 minus u square upon u infinity square into dy. Here delta is equal to 0 to infinity 1 dy. Then boundary layer shape factor h is equal to delta star by theta, and the value of h is equal to 2.59 for laminar flow and h is equal to 1.3 for turbulent flow. Then delta greater than delta star, greater than theta, and less than delta E. This note is very important for the examination. Then there is one more diagram for boundary layer over flat plate. Now the next topic is lift and drag forces. Here drag is equal to shear stress and lift is equal to pressure force. Here normal to the free stream velocity for solid which is circular, then A is equal to pi by 4 into d square. For the second type, A is equal to L into chord, and for the third type plate, A is equal to L into B. Here CL is equal to FL upon half rho u infinity square into A, and CD is equal to FT upon 1 by 2 rho into u infinity square into A. This equation is very important for the drag force. Then after the note is there for velocity separation point, du by dy is equal to 0 and dp by dx greater than 0, then t omega is equal to 0, which are sufficient conditions for the velocity separation. Then here boundary conditions for velocity profile. The boundary condition must be used in the same sequence as given above. So you have to use the same sequence for the examples also. First one is for no slip condition at y of 0 is equal to. Second one is at y of delta u is equal to 0.99 u infinite. Then third one is no variation in velocity beyond delta at y is equal to delta du by dy is equal to 0. Then linear velocity or constant velocity. Here shear stress near to the surface tau is equal to mu into du by dy, which is equal to constant, and tau is equal to mu into d square u by dy square, which is also equal to 0. Then at y is equal to 0, d square u by dy square is equal to 0 and y is equal to delta d square u by dy square is equal to 0. And here one more equation is there. Ft is equal to 3 into pi into mu Vd for Stokes' law. Now the effect of the turbulence on the drag force. Here du by dy turbulent is greater than du by dy laminar, and t omega turbulent is greater than t omega laminar. Then delta star is equal to delta by 3. Then there is one table which is very helpful in the examination. First one is del x is equal to 5x upon under root rex. Then second one is cfx is equal to 0.664 upon rex, which is equal to t w into x upon half rho infinity square, and del x proportional to root x. The curve will be parabolic. Then after the third one is CD is equal to 1.328 upon under root rex, which is equal to ft upon half into rho u infinity square into a. Then for the turbulent flow, first one is del x is equal to 0.38 into x upon rex raised to 1 by 5. Now for the turbulent flow, first one is del x is equal to 0.38x divided by rex raised to 1 by 5, and the cf is equal to 0.058 divided by rex raised to 1 by 5, which is equal to twx upon 1 by 5 rho u infinity square. And third one is CD is equal to 0.074 divided by re raised to 1 by 5, which is equal to fd upon half rho infinity square into a. And here note that del x proportional to c into d proportional to cf proportional to ft proportional to 1 by re raised to 1 by 5. Then after Buckingham Pi Theorem and its application. First one is Buckingham Pi Theorem. For that, m is equal to total number of fundamental dimensions required to describe all n variables, and n is equal to physical variable, and n minus m is equal to dimensionless variables. So in detail you can check out about this method in YouTube or Google. Here we are discussing only the short notes, so we'll include only the fundamental quantities and the advantages. As you can see here, first one is the fundamental quantities. There are mass, length, time, temperature, current, luminous intensity, and the amount of substance. Then there is a note for the Buckingham Pi Theorem. Dimensionless variables such as eta, theta, fraction factor, it should be one of the pi term, and similarly it is two variable having same unit, then ratio of the two is one of the pi term. Then the advantages for the Buckingham Pi Theorem. First one is it reduces the number of variables in the experimental study by huge factor. Then second one is result for full scale product can be predicted by conducting tests on the geometrically same shape of large size. Hence, it reduces the cost of the analysis. The Reynolds Law of Similarities. Here the first one is when the gravitational force is dominant force. So first one is Vr is equal to under root Lr, then second one is AR is equal to 1, third one is QR is equal to LR raised to 5 by 2, then fourth one is TR is equal to under root LR, then fifth one is FR is equal to rho R into LR cube. Then there are some important numbers are there. First one is Reynolds number. Fr is equal to under root Fi by Fg. Then gravitational force Fg is proportional to rho into L cube into G. Then Fi is proportional to rho into V square into L square, which is inertia force. Then second number is Mach number. Ma is equal to, here you can see that value of ma is equal to v by under root k by rho, which is equal to v by c. Then the third one is the Weber number We is equal to inertia force upon the surface tension, which is equal to rho v square L square upon sigma into L. So you can say that We is equal to rho v square L upon sigma. Then fifth one is Euler's number EU is equal to under root IF upon PF. So EU is equal to V by under root P by rho, and T is equal to 2 pi under root L by G. But an equation is there for the vortex motion. You can note down that Z is equal to omega square into R square by 2 into G, and P2 minus P1 is equal to rho into omega square by Z into R2 square minus R1 square. Then for this type of diagram, initial level x plus y is equal to omega square into R square by 2G. Then for the third one, paraboloid of revolution, x is equal to y is equal to omega square into R square upon 4G. Here Vp is equal to half into V of cylinder. Now for the incomplete similarity, Er is equal to mu by Lr and Vr is equal to under root Lr. Then mu r is equal to Lr raised to 3 by 2. This you have to remember. Here similarity laws and the model studies. First one is model must satisfy the certain conditions. In that, first one is geometric similarity. For that, the equation will be like Lm upon Lp is equal to Bm upon Vp is equal to Hm upon Hp is equal to Lr. Here length ratio is equal to Lr. Then area ratio is equal to Ar, which is equal to Lr square. Then kinematic similarity, Vr is equal to Vam upon Vap and Vbm upon Vbp. Here M for the model and P for the prototype. For dimensional similarities, Rem is equal to Rep. Then gravitational force, Fr is equal to V by root GL. Then Reynolds Law of Similarity, here it is used when the viscous force is dominating force in the flow. The first equation is Rem is equal to Rep, which is equal to rho VL by mu, which is equal to VL by mu. Then Vr is equal to mu r by Lr, Qr is equal to mu r into Lr, then Tr is equal to Lr by Vr. Acceleration Ar is equal to mu r square upon Lr cube, and Fr is equal to rho r into mu r square. Then power ratio Pr is equal to rho r into Vr cube upon Lr. So these equations you have to remember, because from these equations the proportionality questions were asked in the examination. For the Reynolds law similarity, or the questions will be like for the closed conduit or pipe flow or flow through pipes or AC ducts, then you have to use these equations. And if the questions will be asked like when the gravitational flow is dominant force, or the examples are like for the open channel flows or flow over a river, then you have to use the similarity which we have discussed earlier, which is for Froday's law similarity. The last chapter is hydraulic turbines. In that, first one is for the Pelton turbine, Hg is equal to H plus Hf, and H is equal to V square by 2G plus Hfn, and V is equal to Cv under root 2Gh. Here Cv is equal to 0.95 to 0.99 for nozzle velocity coefficient. Then force exerted by jet on the bucket, F is equal to rho a V into V minus U into 1 plus K into cos theta. Then V is equal to K into V minus U, where K is equal to bucket friction coefficient. Then torque developed by the runner, T is equal to F into R, and T is equal to rho a V into V minus U into 1 plus K into cos theta into R. Then Rp is equal to F into U, where P is equal to F into D and U is equal to R into omega. Then after hydraulic power, It is power available at the inlet of the nozzle and at the exit of the main stroke, proportional to the net head of the turbine. Here HP is equal to rho g QH, then K is equal to 1 by 2 rho into Q into V square. Then various losses in the Pelton turbine. Here you can see that in the graph there, it is the bar chart. First one is the HP, then after KE, then RP, and that after SP. So the equation will be like, for the efficiency KE by HP, then after eta W is equal to RP by KE, then after eta M is equal to SP upon RP, and eta H is equal to eta N plus eta W. Then eta naught is equal to eta N into eta W into eta M, which is overall efficiency. Then after the condition for the maximum mill efficiency, here eta max is equal to 1 plus k into cos theta by 2. Then speed ratio Ku is equal to u by under root 2 gh, which is equal to u by v, and v is equal to cv into under root 2 gh. Then jet ratio m is equal to capital D by d. Here number of buckets z is equal to 15 plus 0.5 into m. Then this formula is known as the Thugh's formula. Here m is equal to d by d, as you all know. Then t by m is equal to f into r by m, and t by m is equal to 1 plus k into cos theta into r. Now there is the Francis turbine. You can see the diagram for the Francis turbine, and the equation of discharge passing through the runner Q is equal to A into V, then Q is equal to pi into D1 into V1 into VF1, then Q is also equal to pi into D2 into V2 into VF2 for the exit. First one is for the inlet, then after T is equal to rho into Q into R1 into V omega 1 minus R2 into V omega 2. Here the notations are given the above for the each terms. Then after for Francis turbine, VW2 is equal to 0. So T is equal to rho into Q into R1 into VW1, and H into P is equal to rho g QH, which is used for finding the hydraulic power. Then various losses and efficiencies in the Francis turbine. Here the first one is the hydraulic efficiency. Eta H is equal to RP by HP, and eta H is equal to VW1 into V1 upon GH. Then eta M is equal to SP by RP. Then eta naught is equal to eta H into eta M. Here speed ratio Ku is equal to U by V, which is equal to U by under root 2 GH, and flow ratio Kf is equal to Vf1 upon under root 2 GH. From these equations, questions were asked in the exam. Then after similarity laws and model studies. In model analysis, effect of viscosity is ignored, and to equal that effect of ignoring viscosity must be homogeneous conditions should be there. First one is the geometrical similarities. Then after the second one is corresponding velocity triangles should be similar. Now for the geometric similarities, here you can see that by geometric similarity A is proportional to D square and V is equal to CV into under root 2GH. Then U is proportional to root H and ND proportional to root H. From these two equations, questions were asked. Then for Q is equal to A into V, which is equal to pi by 4 into D square H. So Q proportional to D square into root H. Then for power, P is equal to eta into rho g QH. Then P is proportional to Q into H, which is equal to D square into under root H into H. So in general, P is proportional to D square into H raised to 3 by 2. So from the equations of Q, P, U and ND. The relations were asked so many times in the examination, and the most important equation is for the specific speed, and S is equal to N into under root V upon H raised to 5 by 4. So these 5 formulas you should remember for the examination, and there is one example based on that equation. Then for the Pelton, Francis and Kaplan turbine, this table is very important because it includes the various speeds, then after various heads and the discharge of the respective turbines. So for the Pelton turbine, the type of the turbine is impulse and it uses the K, then Ns, which is equal to specific speed, is between 8 to 30, and head is high in this turbine to 50 to 1800 meter. Then for Francis, it is reaction turbine, then speed is 40 to 400 and a medium type of head. Then for Kaplan, it is reaction turbine, speed is 300 to 600 and low head turbine having less than 50 meter capacity. Then after talking about the discharge and the direction about the turbines, first one is for the Pelton turbine, it is low discharge capacity, then tangential direction. Then for Francis, medium discharge and radially inward direction, and for Kaplan turbine, high discharge and axial direction of flow. Then after for Kaplan turbine, here the diagram you can see there, the equation of VW is equal to K by R. Then discharge through the runner, Q is equal to AF into VF. Then VF1 is equal to VF2, which is equal to 4Q by pi into dt square minus ds square. Then speed ratio K is equal to U into T input upon under root 2gh. Then Kf is equal to Vf by root 2gh and Vf is equal to 4 into Q upon pi into dt square minus ds square. Then the next topic is the cavitation, which is the final topic of fluid mechanics. Here in the draft tube, the pressure will be lower and without only the loss in effective head. Using draft tube, P less than PV can be achieved, and for reducing the cavitation of draft tube should not be too much larger, and P mean greater than PV, then sigma greater than sigma C for avoiding the cavitation. So draft tube basically used for decreasing the pressure. Then after Thomas cavitation, parameter is there. Here equation is like sigma is equal to HA minus HS minus HV upon H, and sigma C is equal to HA minus HS max minus HV upon H. Here H is equal to P ATM by rho G. Then HS is equal to height of the draft tube. Here sigma C for the critical cavitation parameter, and HV is equal to PV by rho G, which is equal to vapor pressure head, and H is equal to net head. So this is all about the third chart of the fluid mechanics, in which we have covered all the syllabus of the fluid mechanics. Now we'll start the next subject, which is most important for the mechanical engineering. Subject name is strength of materials.